Okay, this is it. The last chapter, the last swath of notes. We're going to go ahead and blaze through this entire bunch of notes today. It's just one little extra chunk added on to what we already know about T models. And so it makes sense to just go ahead and kill it on one day. And then that's it. It's the last time you have to take notes over new stuff, since we don't have to do chapters 25 and 26. The College Board really has chopped off a substantial bit of content, because they've eliminated 4 tests that we don't have to be able to do, which means it's going to be much easier to decide what kind of test to run on exam day when they ask us to do a hypothesis test, which means they're going to be even more critical if you run the wrong thing, because there's not a lot of wiggle room, a lot of room to mess up on this test, because we have such limited numbers of choices of what types of tests and intervals to do. So here we go. So chapter 22, we first learned the T model with degrees of freedom. We still have a little bit of degrees of freedom that we need to deal with, so that might be a really super short video tomorrow just about degrees of freedom. It would make more sense if we talked about it with a chi-square test, but we're not going to get there. Then we learned that the T model was very much like the normal model. It just tends to be fatter and shorter because it has more variability. If you have very, very, very large sample sizes, T and normal are virtually indistinguishable. And so we learned how to do one sample t-tests and intervals in chapter 22. In chapter 23, we looked at the 2 independent samples and comparing those 2 samples in a hypothesis test or confidence interval. So in chapter 24, once again, you have 2 groups, or sometimes you have matched pairs. So you have 2 sets of data, but they are not independent, and that totally changes the game, because one of the conditions that you check in a 2-sample t-test or interval is that your 2 samples or your 2 treatment groups are independent of each other. Sometimes that is not the case. Sometimes you have things you can pair up. Sometimes you have a before and after study, how much people weighed before the exercise program versus how much they weighed after the program, and all you're doing is comparing the before and after, but you're comparing before and after data for the same people. So you'd pair up the data by person, or subjects, or pairs with an obvious link. Like if you're comparing marrying ages of husbands and wives, then a particular husband and wife are probably, from a particular marriage, are probably not independent of each other. So if you use husband-wife couples in your study, then you would have to pair up the people who are married to each other. Again, back to the matched pairs. You match up pairs of things that are related to each other, and then you have to look at how different the pairs are. So we in this particular section, we talk about data that can be paired up in a very obvious way, before or after for the same people or subjects, husband-wife couples, brothers and sisters, anything where there's not independence and you can have an obvious link. Here's a really big clue. If you have 2 groups and their sample sizes are different, so you have a group of husbands and there's 50 of them, and you have a group of wives and there's 40 of them, obviously you can't pair those up 1-to-1. So if you have different sample sizes, then you have to be in 2 independent sample world. So that's chapter 23 information. There's an obvious pairing of 2 by 2 all of the data in this type of inference procedure. So things and people that are paired up would not be independent of each other. So you can't use 2 sample T methods because you don't have independence. So instead of focusing on 2 groups and how different the 2 groups are, you focus on changes in individuals, so before, after sorts of comparisons, changes, or pair them up and see how different the pairs are. Sometimes there's a period of time, sometimes there's a old data versus new data on the same people, and you just see what the changes were, often over time. Okay, so of course this looks a little crazy. We're not accustomed to Word documents, but it makes a little more sense in this one chapter. So the assumptions and the conditions, they change just a smidgen. Okay, so let's take a really close look. Randomness, still there. That's always going to be there. How many pairs you have is less than 10% of all possible pairs. So there's your 10% condition. We note here that that doesn't apply to experiments. You don't actually have to meet a 10% condition with experiments. But experiments are about, they're not about sampling. You don't sample to get subjects. You get subjects that you can get, and then you randomize your treatments. And then you look at the differences in the pairs and see if those differences are nearly normal. So we either draw a histogram if we are less than 30, and if you're at least 30 pairs, then you can refer to your central limit theorem and say we have a big enough sample size. So these three are the same as all the other inference procedures. What you're going to see here is two added conditions that are specific just for matched pairs. Instead of saying that your two groups are independent, you say the differences are independent. So if you had husband-wife couple number 1, their differences are independent than husband-wife couple number 2, which are independent of husband-wife couple number 3. So your pairs is how you want to think about that. Your pairs are independent. So this is an extra check. And then you need to make sure that you realize that your data are paired. And the gurus say, write it in your conditions. Your data are paired. And that one is sitting first in the list because the data are paired really governs this next check and this check down here. Any of these differences, you're only looking at differences between pairs if you're having paired data. So we're going to add two conditions only to this one type of inference procedure. Okay, so not a big stretch from what we already know. Mechanics, we use a paired t-interval or a paired t-test. That's our name of procedure, as opposed to two-sample t-test or two-sample t-interval. So we have a different name of procedure because we're pairing our data. The null hypothesis always is that the mean of the differences, mean of D is for difference. So we read this, mean of all differences, all possible pairs that we could look at, is 0. Almost always. Occasionally, that might be a different number, but typically we start out assuming that the two groups are, the people or things in your pairs are alike, and so their differences should be nothing. T-score, same formula as always. We're back to the number of pairs minus 1, so this is like sample size minus 1. And so this follows basically the same rule that we had for a one sample t-interval and t-test. And then you'll see that the structure here is the same. Just make a note that the structure is identical to a one sample t. All we did differently was we replaced the y bar with a d bar. Nobody cares about that label. If you call it y bar, it's not going to hurt. But the reality is we're probably going to skip straight to putting numbers in there, in which case we don't have to worry about that label. So the observed mean of the differences minus the mean of the differences that we argued in the null hypothesis. So normally that's a 0 over the standard error, and the standard error, as in the one sample t, is s over the square root of n. So that's a familiar rule that we've used before. And so when you run the mechanics, it's going to feel like you're running a one sample T. The number crunching is going to look exactly the same. Of course, I've already got that one right here, just overlooked it. And then the confidence interval, same structure as we're accustomed to. You start with the mean of your differences. We've been seeing a Y bar here. It's the mean, same as it was before, plus or minus T star with n minus 1 degrees of freedom times the standard error. So it looks identical to the formula for a one sample T, other than just the label is changed, but the structure is all we really care about. We're just going to stick numbers in. So now that we've looked through all that gobbledygook, let's actually work two quick examples. Okay, so first of all, we're going to do the hypothesis test first this time. So we're going to kind of go at things backwards from the way we have been. So I have a theory that on average, and that's a really important word, that's how you know you're in quantitative world, the prices of common grocery items are lower at Walmart than at Kroger. This is old data from several years ago, so these prices have probably changed, probably some of them substantially. In an effort to test my theory, I recently collected information on prices of several items. Test an appropriate hypothesis. Okay, so before we actually write our hypotheses, I'm going to note that this is a paired test because the price of butternut bread should have some relationship between, there should be some connection between how much Kroger charges and how much Walmart charges, because it's made by the same company, they're probably getting their bread from the same source. So those retail prices should have some sort of link. Milk, the store brand of their milk, there should be some relationship, some lack of independence, some association between those two prices. Eggs, we're assuming there's an association between those prices. The price of Tide laundry detergent, there should be an association between those two prices. So if you're comparing like merchandise, you should be arguing that there's a connection between this pair and this pair and this pair and this pair if you're getting the same or equivalent brands. So we no longer have two independent groups. Prices at Kroger and prices at Walmart, they are not independent for the same items. So we can't run a two-sample t-test or do a two-sample interval with this data because we do not have independence between these prices and these prices. They are paired up in a really obvious way. This pair up here in the table screams do a paired test. Okay? Before we run the test, and even before we do the hypotheses, normally if I either add a column if I need to, I've already got one here waiting for me, or even in the calculator, I find the differences. So I could type these in two different columns of a spreadsheet and have the calculator calculate the differences, but it's such a small list, I think I probably will save time if I just find the differences by hand and then just have to key in the one column of data. So I have to decide whether to do Kroger minus Walmart or Walmart minus Kroger. And to help me keep my head straight, I'm going to do left to right because it's just easier for me to keep up with. So Kroger minus Walmart, $2.49 minus $2.14 is 35 cents. $1.29 minus 99 is 30 cents. $1.29 minus 98 cents is 31 cents. $6.99 minus $7.99 is negative $1. 55 minus 44 is 11 cents. $2.49 minus 2.56 is negative 0.077 cents. Ground beef, and this is way the wrong price these days, $3.99 minus $4.12 is negative 13 cents. $3.99 minus $3.58 is positive 41 cents. $2.37 minus $2.47 is negative 10 cents. $2.79 minus $2.98 is negative 19 cents. Negative 48 cents. And 5 cents. Okay, so now we have our list of differences. And it's the list of differences that we're actually going to work with. We are not going to treat these like two separate sets of data. We're going to treat this as one set of differences, and we're going to run inference just on this set of differences. So these are my D's, and the mean of these would be D bar, and the standard deviation of these differences would be S sub D. And in order to get that information, I would need to put this in the calculator and run a procedure. Okay, so I need some space now to write hypotheses and check some conditions. So let's flip over to the next page where we have some space to do that. Oh, if I can get my papers apart. Okay, so hypotheses. We're going to let I'm talking about average prices, average differences, so I'm going to have to define a parameter. So let mu sub D, mu of the differences, equal the mean of differences in prices, and I don't know why I can't get this focused very well. Okay, give me a second. Let me see if I can focus this a little bit better. Oh, it's not wanting to be very friendly today. Okay, that's probably as good as it's going to get. The lighting is just kind of bad. Mean of differences in prices, and I'm going to say Kroger minus Walmart to help me keep my head straight that that's the order that I used. Because I'm not using subscripts for Kroger and Walmart because I'm not treating them as two separate groups. Treating the pairs as individual pieces of data. Okay, so then the null hypothesis is that the mean of the differences is 0. Prices are the same. Unless I have some reason to go in a different direction, that's always going to be my hypothesis. And then the alternative hypothesis is the mean of the differences is well, let's see, what am I thinking? Is it, before I put a not equal to there, I have a theory that the prices of grocery items are lower at Walmart than at Kroger. Oh, I'm arguing that Kroger's more expensive. So this actually needs to be a greater than, because Kroger minus Walmart should be positive if Kroger is more expensive. So the wording that was used in the original problem steers me toward a greater than there. Now, about the subscript, if you don't put the D on, if you just say mu equals, mu equals, mu equals, you should get full credit for this because you're just arguing that you're looking at the mean of a set of data. And as long as you communicate in this, when you define your parameter here, as long as you communicate what you're measuring, if you leave off that subscript, you're going to be okay. So if you find that a little bit awkward, just write mu and don't worry about it. Okay, so now let's do conditions. You change colors. Maybe the blue will show up a little bit better. Okay, so data are obviously paired. Okay, the second new condition is that each of the differences, the difference in the price of bread, the difference in the price of milk, the difference in the price of eggs, the difference in the price of laundry detergent, those differences are independent of each other. So those items come from a variety of different sources, so that's probably true. So we're going to, just to be on the safe side, we're going to assume it that differences in prices are independent. Alright, I have context right there. I didn't get any context in this first one. Let me add a couple words. Data are paired by a grocery item. So we're pairing them up by what the item is. Laundry detergent, eggs, milk, bread. Okay, so those are the two new ones. That's the only real stretch. Everything else is what we've already done. So did we have a random selection of grocery items. No, because it says I collected information on prices of several items. It didn't say they were randomly selected. So we don't know they're random. So we're going to assume that items in the sample are representative of typical purchases. I mean, at the end of the day, I want to know about my grocery bill. So what do I normally buy? Okay, 10% condition. Definitely 12 grocery items is less than 10% of all items. So 12 is less than 10% of all items that can be purchased. Even less than 10% of the things that I would purchase. That's reasonable. And last but not least, the normality condition. Do we have a nearly normal sampling distribution? Well, 12 is way too small a sample size. So we're going to have to look at a picture. So let's go over to the side and let's see what we've got here. We have as low as -$1 for the lowest difference, and the biggest difference looks like 41 cents. So but I've only got 12 items, so I don't want to go with too small a scale, because if I go with too small a scale, I'm going to get way too many bins. I'm not going to see any practical shape at all. So how about 50 cents? Let's count by 50 cent increments. So -$1, -50 cents, 0, +50 cents. And that gets us as big as we possibly would get in this. So these are my differences. And I'm going to just draw a quick sketch. So it looks like in my differences, between -$1 and -50 cents, I only have one observation in that region, and that's the -$1. So I'm going to pick a height to be 1, so that's 1 unit, 1 block tall. And then between -50 and 0, so all the other negatives, 1, 2, 3, 4, looks like there's 5 of those. So I'm going to go 5 times as tall as this. 1, 2, 3, 4, 5, about there. Best guess. That's 6 items so far. Everything else in the positive range between 0 and 50 cents, everything else fits there. All the rest of the data, we didn't have anything bigger than 41 cents. So that means the other 6 differences are all in that last bunch. So here we go. Now, what do I think about that? Well, if I picked a different scale, -$1 might be an outlier. It's not real severe though. It is, however, somewhat skewed to the left. This is not as symmetric or unimodal as I would like. So let me just tell the truth on this last one. The histogram is skewed left. So the sample may not be large enough to yield useful conclusions. Okay, so here's my, I have a problem. My sample size is awfully small. And so here's the deal. In the real world, if I were running a hypothesis test to test something that I want some dependable conclusion for, I would probably go back and get a bigger sample. because this one is clearly not big enough. I can't do that right now. I don't have time. I wasn't given the information to do it. So what do? Well, what I do is what the instructions told me to do. And if I look back at the first page, it said test an appropriate hypothesis. So I've given a big warning right here that you know what, I can run a test, but the results may not be, they might not be great. So I've given the warning, but I'm going to go ahead and finish the procedure, because on the AP exam, if they ask you to run a test, you're going to run the test. Even if the conditions aren't met, you're going to run the test so that you can show them that you know how. Although we're going to say a T model may be useful, so we'll do a paired t-test. Now I'm real iffy about this paired t-test because this last condition didn't check. The only reason I'm going to go ahead and proceed and run it is because I want the points for showing that I know how to do it. But realistically, I should go collect more data. Okay, so because we are in an unrealistic, we need to show how to work the problem situation here, we're going to go ahead and do the mechanics. So mechanics are going to look very much like they do for a single sample. And I'm fitting them in a really small space here, so I'm going to have to be careful with how I use my space. This may be the correct model. Not sure because of that last condition, so I'm going to run the procedure based on this might be. This might just be an anomaly, but we're going to go ahead and proceed anyway. So here are means of differences, D bar. And we're sticking 0 in the middle because that's what we proposed to be the truth and the null hypothesis. And we want to know how different our actual data is, that mean of all the differences from 0. So now I've reached a point where in order to figure out where I am on this curve, I need a t-score. I have 12 pairs of data. So I take 1 away from 12 and I get a degrees of freedom of 11. And so I need a t-score with 11 degrees of freedom, and I'm going to need some statistics from my sample. So that's where my calculator comes in handy. Alright. Here we go. Menu, and that is so fuzzy. I'm so sorry that is not, I can't seem to get it to focus very well today. I actually need a spreadsheet. So let me start a whole new document and hope there's nothing there that I need. And I'm going to put the differences here. So notice I don't need to put in the individual 2 groups because I'm not treating those as independent groups anyway. So I'm skipping straight to the differences. So I had 0.35, 0.30, 0.31, -1, 0.11, -0.07, -0.13, 0.41, -0.10, -0.19, -0.48, 0.05. Okay, so I'm going to run the inference procedure on this data just like I did a 1 sample T. So we'll go to a calculator screen because it's just easier to read that way. And menu, statistics, stat tests, number 7. And there is no 1 sample t-test, there is no paired t-test because they're both the same set of mechanics. So that's why we always use just t-test. You only need something special when you do the 2 independent samples. So we're going to use the data, yeah, and the null is 0. Notice you can change it from 0 here. Which list did we use? Differences. And what was the alternative hypothesis? Greater than. And okay. Alright, so here's all of our numbers that we need. We have degrees of freedom. We have the mean of the observation, which is the first thing we need in our t-score formula. So the mean of the actual samples, x bar, that's kind of fuzzy, is negative 0.037, okay, minus the mean of the null hypothesis, that was 0, over, now we need s over square root of the n. S, it's given, it's s of x is 0.402-ish if we round. So 0.402 divided by the square root of the sample size, which is 12. Make sure you don't confuse the sample size itself with degrees of freedom. Now the calculator has already crunched this number for me. I have a t-score of negative 0.316 approximately. So I'm a little less than a third of a standard deviation below the mean. Not very extreme at all. So one standard deviation below the mean is here. So I'm around here. And I'm looking for a greater than. Okay. Nothing unusual about those differences. Oh, well, I hope if you can see the picture, right? There you go. Nothing unusual about those differences. Huge. Okay. So let's get a p-value. P-value equals the probability of a t greater than negative 0.316, and this is really, really large. According to our calculator, the p-value is 0.621, also in that list. So we get all of the numbers we need for the mechanics from the list. Alright, so 62% is a really, really, really large probability. So we're definitely not going to reject the null. There's nothing interesting going on here. So conclusion, with a p-value of 0.621, I will fail to reject the null hypothesis at alpha equals any reasonable value. I'll just use 0.05. There is no evidence that Kroger prices are higher than Walmart on average. And remember to sneak that word average or mean in there somewhere. Okay, so that was the long piece. We're going to wrap this up with a confidence interval, and then we're finished with notes for the rest of the year. All that's left is just to practice and review and practice and review and practice and review. Okay, last problem. Actually, you know what? Let's do it this way. We will call it a day here and stop this video, and then we will just do example 2 in tomorrow's notes and spread it out. I think that'll work better. So your day 1 homework, and it's not on here, so day 1 homework is also on your list, your master schedule in Schoology, page 648, numbers 1 and 27. So short and sweet. And then tomorrow we'll have notes for the second example and finish up about 4 practice problems from this section and call it done. Have a good rest of the day.